Thank you to the organizers for inviting me. I guess I want to start off by saying that if at any point of my talk there's a word that you don't know the meaning of, probably a lot of the other people won't know the meaning of that, so please feel free to interrupt me and just ask. So yeah, let's get started. I'm going to try and tell you first about what splitting loci are. So the input data is you have a scheme V, and which you can think of as spec R, if you would like. And over it, we consider the trivial P1 bundle, V times P1. And the other piece of input data is I have a vector bundle E. Yeah, I could. But so, I'll start from now. Okay. Right, and given this data, so we know that when you have a vector bundle on just P1, that vector bundle must split as a direct sum of line bundles. And line bundles on P1 are just twisting sheaves, O of something. So this data, when you restrict E to a particular fiber of this map, would give you, sorry? E is a vector bundle over B times P1, which you can restrict to fibers that will give you a stratification. So to describe this stratification, I'm going to write down something that I'll call splitting type. So if I have E, a tuple of R integers like this, where E1 this is ordered in a weakly increasing way, such that the sum of the EIs is equal to D. This data is called a splitting type. So this is a splitting type of rank R and degree D. And then we also define O of this splitting type to be the vector bundle on P1 that is just the direct sum of line bundles corresponding to the integers. Okay, and over here, I forgot to say the starting vector bundle is going to have some rank. I will say it's rank R, and the fiber-wise degree is going to be a constant, and I'll say it has fiber-wise degree D. Okay, and then given the splitting type, I will have a stratum on the base. So this lives inside B, whose close points is some subscheme. But I'll just tell you what the close points are. The close points are those little b and b, such that when you restrict this vector bundle to the fiber corresponding to that close point, this is isomorphic to the vector bundle specified by the splitting type I started with. Okay. So this stratum is in general not going to be a closed subscheme of B, because this vector bundle O of E could degenerate. But there is kind of a canonical way to write down a closed subscheme corresponding to this splitting type. And to do that, I need to tell you about partial order on splitting types. So if E prime and E are both splitting types, then I say that E prime is less than or equal to E if sort of all partial sums are less than or equal. So for all k between 1 and R, if I added E1 prime up to EK prime, that's less than or equal to E1 up to EK. So this is also called the dominance ordering. And over here, I have drawn up the top part of the poset for splitting types of rank 3 and degree 0. So under this ordering, the maximal splitting type is always going to be the most balanced one. So because I have degree 0 rank 3 and 0 is divisible by 3, actually in this case, the most balanced splitting type is perfectly balanced. But if I had degree 1, then the most balanced one will be 0, 0, 1. And as you go down to smaller splitting types in the partial order, what you're doing is you're slightly unbalancing the integers as you're going down. Right, and then the canonical way to write down the closed subscheme corresponding to splitting type E is you just say, oh, sorry, so this is going to be open inside some sigma E bar corresponding to this data, and the closed points are those B, so that when you restrict the vector bundle to this particular P1, well, it's going to split as something, and you require that the thing that it splits as is less than or equal to the splitting type you started with. So this is going to be closed inside B. And sigma E without the bar is in general going to be locally closed. Okay, so this is the first way I'm going to think about splitting loci. But there are two more ways I wanted to tell you about. So I'm interested in the geometry of splitting loci, and if you want to talk about the geometry of something, you have to think about the universal situation. So I have to say the word stack now. So I'm going to let BRD be the moduli stack. But fear not, we'll go to schemes very soon. Moduli stack of vector bundles on P1. So I have to tell you what the stack is, I have to tell you the functor represents. So to give a map, yeah. Yeah, sorry, I don't think of sigma as a sum. I'm just using this as a notation to denote splitting loci. Yeah, so splitting loci corresponding to E, and this input data of a vector bundle is, yeah. Any other questions? Okay, back to stacks. Okay, to give a map from a scheme T, yeah. Yeah, it's related to the geometry of Hagonal curves. There are other reasons too, but that's the quick answer. It's a curve equipped with a degree K map to P1. Yeah. So Bro-Noether theory of those curves for a general such curve is basically the geometry of splitting loci. Yeah. And that's what's called Hurwitz-Bro-Noether theory. Right. So yeah, I want to think about splitting loci in the universal situation. So I have to live on the universal thing that has a vector bundle on it times P1. And the function here is for an input scheme T, to give a map from T to BRD is the same thing as giving a vector bundle E on T times P1 of rank R and fiber-wise degree D. And on this universal space, I can also have kind of a locally closed sigma E. This is now going to be a stack. Living inside BRD, parameterizing families of vector bundles that fiber-wise split as just E. And then, of course, in the universal situation, this is also not going to be closed. And in order to write down the closed substack of BRD, yeah, if you take the closure of the thing that parameterizes fiber-wise O of E vector bundles, then the closure is going to just be the union over all E prime less than or equal to E of sigma E prime. And then this lives inside BRD again. So in the universal situation, I also have like kind of a locally closed substack and a closed substack on my base. And when I say I want to study the geometry of splitting loci, I want to study it in this universal situation. Right. Okay. And then as promised, we can still go back to something concrete. If you don't like stacks, yeah, so that's my third way of thinking about it. If you don't like stacks, you can think about splitting loci in affine spaces. So what does that mean? There exists some smooth cover where you take the disjoint union of certain affine spaces where E is rank R degree D, and this maps surjectively to BRD. Maybe let me explain what this thing here is. So I have end of O of E, which is just a vector bundle on P1. And when you take H1 of that, you just have a vector space. This vector space corresponds to some affine space, and I'm claiming that there exists, so the content of this, there exists a universal, or like there's a canonical way vector bundle on this affine space times P1. And associated to this data, of course, you can, like in the first scenario, form splitting loci on this affine space. And I'm claiming that to study splitting loci in these scenarios for every E is the same as studying splitting loci in the universal situation. Okay, so what is this canonical vector bundle on this affine space times P1? It's a little hard to explain in general, but in the special case, where my E is a bunch of zeros and D, you can check that H1 end of O of E is isomorphic to X1 on P1 of O of D, and then R minus 1 copies of O. And on this affine space times P1, there is a universal extension of O of D by R minus 1 copies of O. And that vector bundle is this canonical vector bundle. And then, right, and then in these like very explicit scenarios, the work of David Eisenbad and Frank Schreier, they write down explicit equations for our splitting loci inside X1 of D O to the R minus 1. So, yeah. This map is smooth. Yeah. Yeah. Like you can, yeah, there exists every map of A mod I to this, including to map from spec A to this, where A is Artinian and I is like square 0. You can lift that map from spec A to. So I think like for this particular case, this means the like Kodara-Spencer map is surjective. So if you like pick a point in this affine space, and you ask, and so okay, if you have a tangent vector to a point in this affine space, that corresponds to a tangent vector on upstairs on like this k adjoint epsilon times P1, and that's a deformation of your vector bundle, right? So tangent space downstairs gives you a tangent space, the app to the map. Okay, tangent space downstairs maps to the abstract deformation space of your vector bundle. You want that map to be surjective. Right, and what these explicit equations are, they are like certain fitting ideals. So, yeah, so in order to cut out sigma E bar, what you do is you require like, like maybe let's go back to this scenario where this is pi. In that arbitrary case, what you want to do is require like rank of R1 pi lower star of E of M to be at least H1 of O of E of M for all integers M. So when I say rank, I'm saying it in like kind of a hand wavy way, but yeah, so if you fix a splitting type here, what you see is if something is a specialization of it, then H1 of it will be at least as large as H1 of the vector bundle you start with. And this is the same for all twists. And actually, this exactly cuts out all the splitting types that are below a certain one. And when you're over a family, when you want to require this, what you do is you just write down kind of a two-term free resolution of this module over your base, and then take the correct determinantal condition on that matrix. And what David and Frank did was they explicitly wrote down what the matrices should be for this very special case where we're working over this particular affine space. Yeah. Which one? O is O on P1, OP1. Can you think about it in that way?
I guess I was just wondering how they compute this X1.
Yeah, I guess this is H1 of by, oh, okay. Yeah, okay. So these are kind of three ways to think about splitting loci. I'm going to jump into a very specific example now, but before I do, I just want to say, like, there are advantages to each of the ways to think about them. I'm thinking about the concept abstractly, think about the stack. When I want to prove anything about them, I reduce to this very nice smooth cover where I just have to work with affine spaces. And when I want to apply them, I have the first scenario where I have an arbitrary base B, but in order to transfer universal properties from the stack to my special base B, I have to prove that the map from B to the stack has nice properties. Okay. So, very concrete example. Yeah, so the case where I really know what's going on is the case where R is equal to 2. So in this case, my smooth covers are going to be things like x1 O of D O. And since this is a D minus 1 dimensional vector space, the affine space I have is AD minus 1. The universal vector bundle on x1 times p1 is the universal extension of O of D by O. So the worst splitting you can have is the split extension. So the origin always corresponds to the splitting 0D. And then generically, you're always going to have the balanced guy. So the question is kind of what is the geometry of all the splittings you can have in the middle? And these equations by David and Frank tell us that if I look at the splitting locus corresponding to some E comma D minus E inside this affine space, this looks like higher secant varieties of the rational normal curve. Of degree D minus 2 inside PD minus 2. Sorry, so the cone over this. So dimensionally, that makes sense. I have some projective object in PD minus 2. When I take the cone over it, I'll live inside AD minus 1. And if I do even more specific example where I take D to be 4, then my affine space is like A3. And so in this case, the possible splittings I can have are like 2, 2, 1, 3, and 0, 0. And like I said, this is the 0, 4. Like I said, the 0, 4 case is just the origin. This is the split extension. So this is 0 inside A3. And then the 2, 2 case is the generic case. In this case, you might ask, what is the geometry of sigma 1, 3 inside A3? And what this theorem is telling us is it's the cone over the rational normal curve of degree 2 in P2. So it's the cone over the smooth quadric. So maybe I can draw this. This is A3 I'm looking inside. Generically, I split as 2, 2. And the cone point is like, but kind of, yeah, everything on this quadric cone I split as 1, 3. Okay, makes sense? Any questions so far? Okay. I guess because this is maybe a commutative algebra crowd, I'll point out one more rank 3 example. So the ideals defining these splitting loci are generally intersections of determinantal varieties. So I guess sums of determinantal ideals, where the matrices are catalecticon matrices. But the kind of curious thing is they're in general like non-transverse intersections, so the codimensions in general don't add. And one example is if you take this splitting type, then the ideal defining this splitting type is going to be the sum of the ideals defining these two. And if you look at all of this inside, maybe I should actually write something. Oh, and I have the brand new eraser. Yeah, so you could try to look at everything inside x1 O of 6 O plus 2. So the geometry of these splitting types are not going to change if you globally twist by some number. So inside here, I can look at sigma bar 0, 2, 4. That's going to correspond to my negative 2, 0, 2 if you twist globally up by 2. And I claim that the ideal defining this is equal to the ideal defining 0, 0, 3, 3, and the ideal defining 1, 1, 4. So this is just these two splitting types twisted globally up by 2. And this first ideal I have to write down some matrices. Right, and then you can think about this as spec of K adjoin A0 through A4, B0 through B4, where the A's and B's correspond to kind of like the two copies of X1 O of 6 O that you have in this vector space. And now I'm going to write down the ideals in terms of these coordinates. 0, 3, 3 is the maximal minors of A0, A4, B0, B4. And then 1, 1, 4 is the maximal minors of this 3 by 6. And this guy and this guy are both codimension 4, but their sum is codimension 5. So the codimensions are not adding, they're very highly non-transverse. Okay. So I think I'll start talking about, yeah, a question? Yeah, it's very special for rank 2. Yeah. But I think it's not. We can chat more about what ideals are what things. I think this one might be secant of something times P1. But yeah, I don't know off the top of my head. Any other questions? Okay. Right. So previously, what's known about these splitting loci was we knew that this is the work of Larson, and Volt. The sigma E bars are normal and Cohen-Macaulay. But what was missing for a long time was the existence of a resolution of singularities for these splitting loci. So as you can see, even in the sigma 1, 3 example, sigma 1, 3 bar is sigma 1, 3, but it's singular along sigma 0, 4. And in this particular example, you know how to resolve the singularities of a cone over a quadric by just blowing up the cone point. But what exactly do you do in general? And can you ascribe modular meaning to what you're doing? And I guess I'll also say that in the case of determinantal loci, the existence of a universal resolution of singularities is key to proving normality, Cohen-Macaulayness, rational singularities, and also producing a free resolution for determinantal ideals. So having a resolution of singularities is kind of important. The origin is always going to be singular, I think. Yeah.
Because it always corresponds to like all zeros at B, or what is that?
So I think you can take the projectivization of H1N and you will have stuff going on there. And then what splitting loci in H1N is the cone over splitting loci in the projectivization. In general, like cones over projective varieties are like kind of the most singular point. So I really expect the cone point to always be singular. Yeah. Yeah, so what I'm going to talk about is like a resolution of singularities. And I guess to do that, I have to define a few things. Right, so yeah, let's like fix some R and D that corresponds to the rank and degree of my vector bundle. And I'll let R lower bar be a sequence of Ri's that kind of are going to be ranks, so that they are weakly decreasing. And then D bar also are going to be a sequence of some degrees. So I just here want DI to be integers. And of course, Ri's are all integers as well. And they have to be non-negative. Given this data, yeah, and also, I guess, given the data of some B and E, a vector bundle on B times P1, I want to define something called F quote that takes in the data of this B, E, and these tuples of R and D. And this is going to be some successive relative quote construction on B. So I'm going to define this. And I'm going to tell you what it is by telling you the functor it represents. So given a scheme T, to give a map from T to F quote is, first you have to give a map from T to B. And given a map from T to B, I can form this fiber diagram. And so the additional data I'll need is I want to specify a flag of subbundles or subsheaves, E1, E2, all the way up to EM. Oh, sorry, I did quotients. So yeah, actually here I want that's not equal to R. You'll see why in a sec. Yeah, I want a flag of subs all the way including into F tilde pullback of E. So I pull E back from B times P1 to T times P1, and then I have to give this like flag of subsheaves with the condition that the rank of EI is Ri, and the degree of EI fiber-wise is DI, and then also a flatness condition. So F tilde pullback of E mod EI should be flat over T. So, and then I'll have to quotient by an equivalence where I say two flags are the same if there are isomorphisms between the EIs that commutes with the identity on the pullback of E. So this is F quote. It's some scheme when you start with a scheme B that maps to B. And I'm going to try to use this construction to resolve the singularities of my splitting loci. But I'm going to need one more definition. So yeah, I'm going to say that if I have a flag of vector bundles on P1 is called admissible if there are two different conditions. So the first condition is, so I'm going to call this EM plus 1. First condition is EI plus 1 mod EI. Not only has to be a vector bundle, but also a balanced vector bundle. So things like 0, 0, 1 is balanced, 0, 0, 2 is not. And also up to automorphism of EI the inclusion of EI inside EI plus 1 is unique. So when all this happens, the flag is admissible. In general, there is always going to be an admissible flag called the Harder-Narasimhan flag of subbundles. But for some special splitting types E, you can have more than one admissible flag. So let's do some examples. I promise that these conditions are actually quite obvious numerically. Okay, maybe I'll look at my notes. Yeah, I could do O of 4, including into O of 3, 4, including into O of 0, 3, 4. Maybe let's check the condition. So for example, the first quotient O of 3, 4 by O of 4 is just O of 3. It's a line bundle, of course, it's balanced. The inclusion of O of 4 into O of 3, 4 up to automorphism of O of 4 is always just going to be including into the second summand because there are no maps from O of 4 to O of 3. And in general, if you kind of cut off your splitting type at some point so that the smallest one on the right is bigger than the largest one on the left, then the inclusion of the right half is going to be unique up to automorphism of the sub. So this is admissible. And let's do a more relaxed flag. Oh, and also, if you know, this is also the Harder-Narasimhan flag of subbundles for O034. But in general, you can have coarsenings of that flag and still be okay. So, for example, if you take this flag, then the quotient of the largest guy by the second guy is O of -4, -3, -3, which is not perfectly balanced, so it's not semi-stable, but it's still allowed because I was only requiring it to be a balanced vector bundle in my definition for admissible flags. So these are some examples of what would work. And then lastly, I want to say that a tuple R and D is called E admissible if there exists such a flag for O of E, which is admissible and has ranks and degrees specified by my R and D. So, okay. Any questions about these definitions? Right, and then equipped with these definitions, I can now state the resolution of singularities I form. So let's start with RD E admissible. Then let's define sigma E tilde RD to be this F quote construction formed on the universal moduli stack with these particular numerical data. Yeah, so I'll do BRD, and then on BRD times P1, there's some universal vector bundle, and I ask for the stack that parameterizes flags of subs with flag quotients specified by R and D. So this thing is going to map to BRD because F quote is just always going to map to the base. But the claim is it maps surjectively to sigma E bar. And moreover, if you base change this whole thing to the open where it splits as exactly E and not some E prime. I call this phi. Then the pullback is going to be an isomorphism. So that's the first part. This is what the resolution of singularities should look like. It's an isomorphism over a dense open. And it's surjective onto the thing I want to resolve. And then, moreover, this guy is smooth and irreducible. So maybe an asterisk here. Yeah, algebraic stack. So if you don't know what that means, you can just imagine we're doing this construction on H1 and of over E, O of E. Imagine the cone, and I'm resolving sigma 1, 3 by taking O of 3 subsheaves of the vector bundle. And the statement is saying that when you make that construction, you'll always get some birational smooth scheme resolving the singularities of your base. Right. And then using this theorem, we're able to do some computations. But to tell you about them, I have to first define what a tame splitting type is. So if E is a splitting type, we call it tame if you can write E as the concatenation of two splitting types such that F and G are both balanced. And this condition is equivalent to you can always find a one-step flag which is admissible. And in this particular scenario, and also assuming K is algebraically closed, characteristic 0, I was able to show that tame splitting loci have rational singularities. I guess I have about 7 more minutes left. Do people have any questions about this so far?
Universal bundle, is it and this is it the O1 or O minus 1 in the projecting? Is it that is something else?
It's rank R and fiberized degree D. So it lives on, so you have BRD, and then over it you have BRD times P1. And then there's some vector bundle here, E unit. It's rank R, and when you restrict it to a P1, it's degree D. So that, yeah, like if you have a scheme T that has a map to BRD, then the data of that is a vector bundle on T times P1, and that vector bundle is pulled back from this. Yeah. And yes.
This F4, can you say something about the first theorem as to what is the hard part and?
Yeah. So irreducibility is true for all F quote, not assuming admissibility, like inadmissible, whatever, not assuming anything about R and D. So what's really used there is a very explicit understanding of, okay, vector. And to show irreducibility, or what we actually show is when you have a good base B, then this construction is irreducible. And good means the codimension of each splitting locus is as expected, and also each splitting locus is irreducible. And then to show the irreducibility of F quote construction over such a good base, what you do is you have this relative kind of hyperquote construction, you can embed it inside a fiber bundle, fibering in absolute quote, and it's cut out there by the section of a vector bundle, and the codimension is exactly the rank of that vector bundle. So you can do some dimension counting. Yeah, you stratify the thing that you want to show is irreducible into irreducible pieces, and you check that there's only one piece that has the expected codimension. So it has to be dense inside the thing you want to show is irreducible, and the thing has to be reducible. So that's the irreducibility part. And smoothness. So yeah, I think irreducibility is a truly genus zero phenomenon. Smoothness is true for all curves, I think, where you replace BRD here with the stack of vector bundles on a fixed genus G curves, and the splitting loci are replaced by certain Harder-Nara-Simons strata. But in that case, you only have smoothness and you don't know irreducibility. So you know that there's one component resolving the singularities of the Harder-Nara-Simons strata, but there might be more components. Yeah.
Get both smoothness and reducible simultaneously, is that what you're saying?
I need E admissible for smoothness. Or sorry, I need E admissible for birational over the open. I think I also need it for smoothness. So what's happening is when E is admissible, or sorry, when R and D are admissible, then there is a unique such flag for O of E up to kind of automorphisms of the sub. So like if you look at 0, 3, 4, and it asks for a sub like this, or asks for a flag like this, there's no other one you can write down. You're kind of forced to write this one down. But if you, let's actually forget about rank 3, like just think about rank 2, right? So the distinguished flag for O of 0, 2 is this guy. There's a unique inclusion of O of 2 into O of 0, 2. If I unbalance this a little bit, and I have -1, 3, and I ask for O of 2 inclusions into this, that's a P1 worth, wait, actually. Yeah, that's a P1 worth of flags. You take hom of O of 2 to O of 3, that's a two-dimensional vector space, but up to scaling, I am considering them the same, so it's P1. And you also throw out the 0 because I want inclusions, so it has to be a non-zero map from O of 2 to O of 3. Yeah, so you really need E admissibility for this part, and then for the tangent space dimension counting to prove smoothness, you also need the admissible. Yeah, I think maybe instead of saying anything about the proof for the rational singularities thing, I'll say a little bit about why we care. So yeah, previously I mentioned a little bit about Hurwitz-Brown-Noether theory for a general K-gonal curve. So for a general curve of genus G equipped with map to P1, so general in the Hurwitz space. The Brown-Noether theory of that curve is controlled by these splitting loci. And what is happening is if you have a line bundle on that curve, maybe I should write a little bit. Let's say you have some K1, and C is smooth and proper and all the good things. And if you have a line bundle on C of degree B, you can form its push forward under this map. And one can show that this is a rank K vector bundle on P1. So this is going to have some splitting type. And using this correspondence, you can kind of annotate pick D with splitting types. And this works really well with the classical Brown-Noether theory, where you care about line bundles with at least some number of sections. because H0 of L is H0 of F push forward of L. So if you in particular cared about line bundles with some number of sections, you will just have to require that the splitting types you have correspond to vector bundles with some number of sections. And yeah, and Hurwitz-Brown-Noether theory is really cool because it recovers classical Brown-Noether theory. If you take K to be sufficiently large, you can recover all the theorems of classical Brown-Noether theory from the results of Hurwitz-Brown-Noether theory. But what was missing previously was, for example, in classical Brown-Noether theory, you have GRD, which comes from the resolution of singularities for determinantal loci. But you don't have a resolution of singularities for splitting loci. So you can't recover anything that's like, for example, the Giesecke-Petri theorem that says GRD is smooth for a general curve of genus G. You can't recover from Hurwitz-Brown-Noether theory. And now we can. Like the first theorem that proves the smoothness of these resolutions, this construction restricts to GRD when you take K to be sufficiently large and C to be a general genus G curve. And then also, why do we care about these like really special splitting types that are tame? That's because they correspond to components of WRD for a general K-gonal curve. So the second theorem specializes in this particular setting to tell you that if you have a general K-gonal curve of genus G, then the components of its Brown-Noether variety WRD have rational singularities. Okay, I think I'll stop there. Thank you.
That theorem of David and Frank, is there any hope of getting something similar to like a different type that's not symmetric?
I think so. So this paper is called Relative Violence in you coded okay. Yeah, but I think what they do really in that paper is like a very general statement that says there is this monad that is supposed to represent like higher push forwards. So yeah, like I said, we want to kind of take fitting ideals of this module. And I think the machine of their paper should do this for any base. But in the explicit case of X1 OV and O's, they wrote down the example in the paper. And then I was just like, okay, I'll reap the benefits and be able to read it off. But I think, yeah, in H1NE, which I think is really the correct setting, you should also be able to write down certain, I would expect Catalectican matrices and determinantal conditions that cut it out. Yeah, I think that's a really interesting question. Yeah.
So here with the things when outside as rational order, there's something that like for like maybe still like a other close characteristics go like to classify that order.
Yeah. I have no idea what is happening when it's not tame. Like even, and the reason is if you want to say something about one splitting type, you have to look kind of infinitely deep into the cover of affine spaces. So if you cared about like 0 to 4, you can look at it inside. You have to look at it inside first, like maybe X1 of 6. Yeah, okay. Maybe a different way to say this is you have to think of it as 0 to 4 and then like make it live inside the correct X space, and then you have to think about it as 1, 3, 5, and 2, and so on. So there's kind of no way to check infinitely many examples before Macaulay 2 cries and breaks. So I actually don't know any example or non-example in the case of not tame where I know it has like rational singularities or not. Yeah, and I'm really curious about what's happening in characteristic P too. And here the reliance on K equals K bar characteristic 0 is because I really needed to use the Borel-Weber theorem, which is not known in characteristic P and might behave terribly. Yeah, so I also have no idea what's happening in characteristic P, and it might be an interesting question for people who are interested.